What if the next battery revolution doesn't depend on rare minerals, futuristic solid-state cells, or billion-dollar labs? What if it comes from something already on your kitchen table? Sodium. The same element we know from table salt is now at the centre of the world's most important battery race. Lithium-ion batteries have powered our technology and vehicles for decades, helping drive the clean tech economy, but they depend on expensive and tightly controlled supply chains. Sodium-ion batteries offer something different: cheaper materials, wider supply chains, better performance in cold weather, and possibly safer storage on a large scale. However, there's a catch. They are heavier, store less energy, and their lifespan is still being improved. Meanwhile, lithium-ion batteries are also getting better. So the real question isn't, are sodium-ion batteries better? The real question is, where are they better, and can they arrive soon enough to make a difference?
Everyone is familiar with lithium-ion batteries. We are using them in our cell phone, laptop. Some of us are driving electric cars. The working principles for sodium-ion batteries is similar to that of lithium-ion. The only differences is that the working ions, the ion that's moving between the positive and negative electrode, is sodium instead of lithium.
A sodium-ion battery works much like a lithium-ion battery. There's a cathode, an anode, an electrolyte, a separator, current collectors, and ions moving back and forth. But sodium ions do the work, not lithium ions. Lithium and sodium are in the same column on the periodic table, so the chemistry is similar, but sodium is larger and heavier, and that changes a lot. Larger ions are harder to fit in. They take up more space inside the electrodes, which usually means lower energy density or less energy per kilogram or litre. The thing is, sodium-ion batteries are not new. Researchers have studied them for decades. However, lithium became the dominant technology. But what are the reasons for this, and why are we going back to looking at what seems like a worse technology on paper? In recent years, the focus has shifted from gas cars and fossil fuels to electric cars and renewable energy like wind and solar. All of these are highly dependent on batteries. Throw into the mix cell phones, laptops, and other consumer tech which needs to run for as long as possible while remaining as small as possible. Lithium-ion batteries became dominant because they represent the most energy-dense solution and were able to be scaled up and manufactured with decreasing costs to the end user. The International Energy Agency reports lithium-ion battery prices dropped sharply from 2010 to 2023. More innovation could lower costs by another 40% by 2030. Sodium-ion offers a different strategy: reduce dependence on critical materials and build batteries from more widely available resources. Sodium-ion batteries rely on sodium compounds derived from abundant raw materials, such as soda ash, and that this abundance could help ease supply chain pressures and diversify the battery landscape.
The driving force for us to work on sodium-ion batteries is to be able to utilize this element, sodium, that is widely available on the planet Earth. We want to minimize the use of critical materials such as nickel, cobalt, copper, like as the current collector. So sodium actually, we don't need to use the copper current collector anymore. Aluminum can be used on both positive and negative electrode.
Sodium-ion may never match the range of advanced lithium-ion cells for EVs, but energy density is not the only factor worth considering. Battery designers consider cost, power, cycle life, safety, temperature, manufacturing yield, charge rate, recyclability, and supply chain resilience. A battery with lower energy density can still be useful if it's cheaper, safer, lasts longer, or is designed for certain uses. That's why sodium-ion is especially interesting for grid storage, short-range EVs, electric two-wheelers, commercial fleets, low-temperature applications, lead-acid replacement, backup power, power tools, and hybrid battery packs. CATL, the world's largest battery maker, announced its Naxtra sodium-ion battery in 2025, claiming 175 watt-hours per kilogram at the cell level. In comparison, CATL manufactures lithium-ion batteries with an energy density of 205 to 330 watt-hours per kilogram. Not too far off. The first commercial battery has now been rolled out in the Chang'an Nevo A06, claiming 400 kilometers or 249 miles of range from its 45 kilowatt-hour sodium-ion battery. and it should be capable of fast charging from 30% to 80% in just 15 minutes. This is surprisingly already on par with many contemporary lithium-ion based cars on the market today, especially towards the lower end of the market. Meanwhile, CATL claims it can achieve over 10,000 charging cycles, which is actually more than a lot of lithium-ion batteries, which quote 500 to 1500 cycles, depending on the specific tech. CATL describes the chemistry as cheaper and more abundant than lithium, with lower fire risks in EVs. While the range of sodium is lower, it appears to be enough for most applications. Sodium ion has one big performance advantage, however.
Like many things in the world, that bigger doesn't mean slower. Bigger can be fast. So sodium ion actually, if you made it correctly, in the solid state, the sodium ions can be transported very quickly. So the power of the batteries can surpass lithium ion, especially at extremely low temperature, like below 0 degrees Celsius, up to below -20, -30 degrees Celsius.
Sodium ion's biggest strength right now is how well it works in the cold. Anyone who's driven an EV in winter knows batteries don't like the cold. Chemical reactions slow, charging is harder, and range drops. Sodium ion batteries may perform well in cold environments because sodium ion can move quickly under certain conditions, allowing high power even at low temperatures. While lithium ion batteries lose up to 80% of their energy capacity at sub-zero temperatures, sodium ion maintains high efficiency in extreme cold, down to -40 degrees Fahrenheit. This could make sodium ion batteries especially useful in northern climates. Sodium ion looks on paper like it should be more environmentally friendly, but is this actually the case in practice? The answer is potentially yes, but not automatically. A battery's environmental footprint depends on the full life cycle. For lithium-ion batteries, environmental concerns often focus around mining, water use, energy-intensive refining, and the concentration of key materials like lithium, cobalt, nickel, and graphite. Lithium often relies on harsh chemicals like sulfuric acid and sodium hydroxide to extract. Toxic chemicals and brines can be released into nearby soils and streams and can require up to 2.2 million litres of water per tonne of produced lithium. Sodium ion can reduce pressures on some of those processes and materials, especially if chemistries avoid nickel and cobalt and use more abundant elements such as iron, manganese, and aluminum. However, they still suffer in other areas. Less energy density means a heavier end product for the same energy output. This actually results in higher CO2 emissions from manufacturing and shipping than lithium, for example. Sodium is considered more eco-friendly over its life cycle, but there are still some challenges. Sodium-ion batteries often use hard carbon anodes, and producing high-quality hard carbon at scale is not trivial. Cathode choices vary. Layered oxides, Prussian white or Prussian blue analogues and polyanionic compounds all have different trade-offs in cost, stability, voltage, manufacturability, and performance. And making batteries at scale is extremely difficult.
From the materials perspective, the components should be cheaper if it's scaled up. In terms of the ease of manufacturing, I think the overall mistake the West have made for the past decade is that to underestimate how difficult it is to make billions of cells with consistent quality and great yield. Making high-end rechargeable batteries is as difficult as making high-end computer chips.
That comparison to computer chips is not an exaggeration. Modern battery factories are precise manufacturing systems. A minor contamination issue, uneven coating, poor moisture control, or an inconsistent formation process can compromise performance and safety.
Currently in lithium-ion batteries, there's some geopolitical issues and competition in terms of the dominance of certain country. We just want to level the playing field that countries like India, Kenya, let's say they all have a fair chance for their electrification of their society. So I think sodium-ion batteries provide such an opportunity.
Sodium ion is not just about technology, it's about global politics and development. Lithium-ion supply chains are powerful, but they're not evenly distributed, with China owning 60 to 70% of raw material refining, over 75% of battery cell manufacturing, and over 90% of anode and electrolyte production. Lithium is only mined in a handful of countries like Australia, Chile, and China. Nickel, cobalt, copper, and graphite also face similar issues. Price volatility, geopolitical risks, and bottlenecks can impact all of these materials. Sodium-ion could open up the door to more distributed manufacturing, especially if it can use more common materials and adapt to existing production equipment. Salt, for example, could be pulled directly from the ocean, opening up extraction to many more countries, creating less distance travelled for materials and more localised battery production. That could matter not only for EVs but for the electrification of emerging markets, rural storage, telecom backup, microgrids, and affordable mobility. However, the biggest mistake would be expecting sodium-ion to replace every lithium-ion battery. That's not how the battery market works. Different chemistries win at different jobs. The best fit application for sodium-ion are grid-scale storage where weight and volume are less important. They represent up to 20% reduction in capital cost compared to lithium-ion. They have a significantly lower risk of thermal runaway and fire compared to lithium chemistries. Due to their excellent thermal stability systems, they can function with passive cooling. This eliminates energy-intensive, active HVAC cooling loops, shrinking operation overheads. Small city cars, delivery vehicles, low-cost EVs, and urban fleets do not always need 600 kilometers of range. If savings are significant, many people and companies may prefer this option. In many countries, the fastest electrification may happen through scooters, motorcycles, rickshaws, and small commercial vehicles.
In several niche markets, sodium can show some advantages. So things like power tools, where the extreme high power are required, low temperature performances, start-stop. Sodium's first product line can be quite successful, in my opinion, is to replacing the lead acid. The cycle life is very limited, and every 2 or 3 years you have to change your batteries, and it's actually quite heavy.
For some of these use cases, cost is a dominant factor, and while sodium-ion appears to be cheaper in theory, there is one big problem. Lithium-ion keeps getting cheaper. Lithium-ion has enormous advantages: decades of manufacturing experience, massive factories, refined supply chains, high energy density, known performance, and continuous innovation. LFP batteries in particular have already reduced reliance on nickel and cobalt. That weakens one of sodium-ion's selling points.
I think sodium really have an uphill battle is that the cost of lithium keeps coming down. We made the promise to the society that the sodium will eventually be cheaper, but how long it takes sodium to get there, that's the part hard to predict.
That is why sodium-ion batteries will probably be used first in markets where they offer more than just lower cost, like better cold performance, safety, use of local materials, or replacing lead-acid batteries. The future will probably not be about one battery chemistry replacing another, maybe a mix of different battery types working together. Solid-state batteries could transform high-end EVs if they solve manufacturing, costs, interface stability, and scaling challenges. Lithium-sulfur has a huge theoretical energy density, but major durability and commercialization hurdles. Flow batteries and iron-air systems could become important for long-duration grid storage, but they are not direct replacements for EV batteries. So sodium-ion's future depends on timing and application. If sodium-ion can reach real markets quickly, especially for grid storage, low-cost vehicles, and replacing lead-acid batteries, it does not have to outperform every future battery chemistry. But if it takes too long, lithium-ion may keep improving and newer technologies may capture the most attractive niches.
The humanity needs a lot more electrochemical devices that can convert and store energy. The biggest challenge for me is really the shift back to burning of fossils in order to support the AI growth, support the competence. I think it's very short-sighted because electrification is really a more efficient technology. The energy conversion efficiency for batteries is more than 90%. Very few technologies can perform that storage and conversion duty.
So, will sodium-ion battery technology be the answer to cheaper and more efficient batteries for vehicles and other uses? To be honest, the answer is yes, but only for the right uses. No, sodium-ion probably will not replace lithium-ion in the whole EV market anytime soon. No, it's not the best choice for every high-performance or long-range vehicle. And no, lower material costs do not always mean lower battery costs when making them at large scale. But sodium-ion could still be a very important part of the battery world. It could help make grid storage cheaper, It could replace lead acid batteries in many uses. It could support affordable EVs, commercial fleets, two-wheelers, and cold weather applications. It could reduce pressures on supply chain for lithium, nickel, cobalt, and copper. It could give more countries a realistic path to battery manufacturing. The future of batteries probably will not be just about one chemistry. It's about a whole ecosystem of engineering solutions, and sodium ion may be one of the most practical, scalable, and overlooked parts of that ecosystem. The next big battery breakthrough might not come from finding something rare. It might be about learning how to use something much more common.